In our previous lesson, we defined continuity at a point. The limit of f of x as x approaches c is equal to f of c. In other words, the limit of the function as x approaches some real number c is equal to the value of the function at c. We also defined continuity on an open interval and said that a function is continuous on the open interval from a to b if it's continuous at every point in the interval. Now let's take a look at continuity on a closed interval. We say that for a function to be continuous on the closed interval ab, f has to be continuous on the open interval ab. F is continuous at every point in the interior of AB. Now for the endpoints, we require it to be continuous from the right of A and from the left of B. We can also have functions that are continuous at half-open intervals, such as an interval that's open at A and closed at B, or closed at A and open at B. For all these cases, f has to be continuous on the interior of the interval, and left or right continuous on the closed endpoints of the interval. Let's look at some examples. At what interval is this function continuous? The domain of f is in the closed interval, -1, 1. This function is continuous at all points in the open interval, -1, 1. It's also continuous on the left endpoint as x approaches -1 from the right. So the limit of the function at that point is also equal to the value of the function at that point. And the limit of the right endpoint as x approaches 1 from the left also exists and has the same value of f of 1. Therefore, by our definition, we can conclude that f is continuous on the closed interval, -1, 1. Let's take a look at one more example using the greatest integer function. Sometimes this is known as the floor function. You might also see the greatest integer function written like this. You should be able to recognize and use any of these notations. The greatest integer function is a common type of step function. Looks like this. Go ahead, pause your video and describe the continuity of this function. Remember, for a function to be continuous at x equals c, the limit as x approaches c must exist and also be equal to the value of the function at x equals c. So this function has a discontinuity at every integer. Let's take a look at when x is equal to 1. The left side limit is 0, and the right side limit is 1. And the value of f of 1 is 1. Now the function is continuous at every other point, just not at the integers. For example, if we took the point c is equal to 2.5, the left side limit is 2. And as x approaches 2.5 from the right, the limit is also 2, which is equal to the value of the function at 2.5. Again, this function is discontinuous at every integer, but is continuous at every other real number. Let's do one more. Pause your video and describe the continuity of the function g of x. As we approach x equals 0 from the right is continuous. This part of the graph doesn't look like it ever reaches 2. And the same thing at x equals 3 from the right is continuous. And g is not defined at x equals 4.